the Kelvin, and the mass of each molecule is 5.3 times 10 to the minus 26 kilograms. What you want to find out is the speed of a typical molecule. Well, we have an equation for that. Half the mass times the average square velocity is equal to 3 over 2 times k times the temperature. So if you have a typical speed of a gas molecule, you're going to want to find out the square root of the average square velocity, which is equal to the square root of 3 times k times the temperature divided by the mass. In this case, that works out to 484 meters per second.
So it's actually kind of cool. This is something that you would do like later on, like a higher level class. But maybe I want you to see here is that so you can use that formula to do two things. One, to equate the temperature with the motion of the molecules of the substance, right? So that's very important. Two, you can use that, what she's talking about, that root mean squared, is like you're kind of like using statistics to get a better idea. And what you notice here is that the average molecule in a gas is moving about 484 meters per second. That's pretty crazy. That's pretty close to 1,000 miles per hour, right? If you think about the little tiny gas molecules that we're breathing out, in and out, that are flying around the room, the average one is moving faster than an airplane, right? Which is kind of crazy. Now, granted, average means that a lot of them are moving slower than that, and a lot of them are moving faster than that. So some of them are moving even faster, right? Which is kind of wild when you think about it. But they're such tiny little objects that it's not difficult to get them moving fast. You know what I mean? So later on we'll learn some physics and we'll learn especially more about the kinetic energy equation. But the idea is that like this if you took the motion of each little gas molecule in here, right? Like each little oxygen or nitrogen molecule or carbon dioxide or whatever that's floating around, and you track its motion, you could sort of average out and add up all the little kinetic energies, and it's actually going to tell you something about the temperature of the room, which is kind of weird, right? You think about that, but that's really all this is telling us, is that the temperature of the gas is related to the motion of the gas particles, right? So the faster they're moving, guess what? The hotter it's going to feel like, right? So we actually says that as heat, right? So if you go like to Las Vegas on a hot summer day, a much higher temperature, say like 112 degrees Fahrenheit, really tells you something about the way that air molecules are moving in that environment. Does that make sense? So that's the kind of the main thing I want you to think about here. That's really fast when you think about it.
But 484 meters per second isn't the average speed, it's the root mean square speed. So how does the root mean square speed compare to the actual speed of the molecules in the gas? So back in 1859, Scottish physicist James Clerk Maxwell used statistical analysis to figure out the distribution of speeds in an ideal gas. And it looks like this. The top of the curve shows the speed that's close to the speed of the greatest number of molecules, and the root mean square speed is slightly to the right of that. So the molecules in an ideal gas can actually have a whole range of different speeds, but most of them are pretty close to the root mean square speed. So it's a useful way to get a picture of how fast a gas's molecules are moving. Now, we've seen the smooth, even way that pressure and volume change with temperature in an ideal gas. So gases aren't always like this. When the pressure gets too high and the temperature too low, they start to act very strange. High pressure is a problem because it forces molecules together to the point where they start to interact. Low temperature is an issue for similar reasons. The molecules have less kinetic energy, they're moving around less energetically, so their attraction to each other starts to have an effect. And remember, we said that one of our assumptions about ideal gases was that they don't have forces acting between molecules. They just bounce off each other like ping pong balls. So at higher pressures and lower temperatures, real gases tend to have a bit less volume than ideal gases would. And at really high pressures and really low temperatures, gases just start acting weird. And then eventually they aren't even gases anymore. At a certain point, the attraction between the molecules takes over and stops them from bouncing around so much. They become slightly more ordered and take the form that we call a liquid. It's like when water vapor from the air condenses on the outside of your nice cool glass of orange juice, kind of making it look like it's sweating. Increase the pressure or lower the temperature even more, and the attraction between the molecules has even more of an effect. The liquid freezes into a solid. In the same way, lowering the solid's pressure or raising its temperature will eventually make it melt into a liquid and then boil into a gas. Well, usually. Take a look at this diagram. It shows the different phases of water depending on its pressure and temperature. The vertical axis shows pressure, so the higher up you go in the diagram, the more pressure there is. The horizontal axis shows temperature, so the farther you are to the right, the higher the temperature. Below the diagonal line, so at low pressures and high temperatures, water takes the form of water vapor, a gas. So the left of the line is nearly vertical, water's ice, a solid, and at the pressures and temperatures represented by the triangle in the middle, water is a liquid. But you'll notice.
Alright, so here's another technical chart, right? So one of the things this is showing us is that the state of matter does not just depend on temperature, but also depends on pressure, right? And so typically when we talk about pressure, you can think of that as like, for us it's air pressure, right? So this is measured in ATM, which are atmospheres, right? So the air pressure that you experience right now is 1 atmosphere of pressure, right? If you've ever gone underwater, right? You dive down like 10 feet, like your ears start to hurt a little bit, equalize your pressure, right? Because there's a lot more pressure down underwater. Then you go further and further down, like say in the ocean, the pressure increases really. So it's just the weight of all of those molecules kind of like pushing down on us, right? So one thing that's weird about air pressure is like there's like a whole atmosphere pushing in on us, right? And then our insides are actually pushing out the same force, so it's equilibrium there. But you can change that. You can go to a different location, or like even in an experiment, you can change the pressure that's acting on the substance inside of like a container or something, for example. And I'll show you a demonstration of that. But the idea is that you can control temperature and pressure, and it's going to determine whether or not, and this is for water, it's going to be a solid, a liquid, or a gas, right? So he's going to kind of talk about this and go to a couple of key points.
So there's a point toward the top right, labeled the critical point. On a phase diagram, the critical point represents the maximum temperature and pressure where the substance can be a liquid. For a gas to become a liquid, it has to be below a certain temperature, known as the critical temperature. For water, the critical temperature is about 647 Kelvin. Above the critical temperature, you can increase the pressure as much as you want, but the gas will never condense into a liquid. There's a critical pressure too, which for water is about 22 megapascals. If the pressure is above the critical pressure, you can raise the temperature as much as you want, but the liquid will never boil. Then there's a point towards the bottom left where the two lines intersect. That's the triple point. And that's what Marin and I use to map out Mars. The triple point is the temperature and pressure at which a substance coexists as a solid, liquid, and a gas. It's also what we use to define the Kelvin temperature scale. The triple point of water is 6.105 millibars and exactly 273.16 Kelvin. That pressure and temperature is special because at thermal equilibrium, water can exist in 3 phases at once: ice, gaseous, liquid, and vapor. Now you'll notice on the diagram that at pressures and temperatures below the triple point, there's only the gas phase and the solid phase. That's because below its triple point, a substance can't actually take liquid form. Instead, it's either a gas or a solid, and it transitions directly from one to the other. A process that's known as sublimation if it goes from solid to gas, and deposition if it goes from gas to solid. That's why dry ice, which is made up of carbon dioxide, vaporizes directly to gas. The triple point of carbon dioxide is about 5 times atmospheric pressure, so liquid carbon dioxide can't naturally exist on Earth. The triple point of water is used to define the Kelvin temperature scale because it's consistent. You just find a temperature where you get 3 phases of water at once, which scientists have said to be 273.16 Kelvin by definition. It also made a lot of sense for the Mariner 9 mission to use the pressure of the triple point of water as a reference point for its Martian maps. One of our main goals in exploring Mars has always been to search for evidence of life, either now or in the past. And as far as we know, life needs liquid water. Since the reference point for Martian altitudes was the triple point of water, liquid water couldn't exist at altitudes above the reference point, where the pressure would be too low. That made it easy to see on a map all the places where liquid water could be, or have been, and where life could possibly survive, or have survived. Today you learned about the kinetic theory of gases and how to calculate the root mean square speed. We also talked about the phase changes, including the critical point, the triple point, and how that all applies on Mars. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel.
Alright, so that was a lot of info. But, do you have any questions?